Hello, how we doing? Moving on today to talking about the types of chemical reactions that we can see. For this part of the year, we're up to 5 that we're gonna have to be able to recognize after today. I'm gonna do some notes with it. I'm gonna push a gizmo at you as well to try to get you to, understand and get the practice that you need to get this. All right. Sometime in the near future, I will have demos of each of these reactions. I just can't go back and forth between video and this. So I don't know if it'll be Friday or whatever, but we'll see when it is. Okay, first things first, you have a bell ringer. I'm not going to leave a lot of time to do this right now. Pause the video, answer it. I will ask you the question on Edpuzzle. All right, but to balance this, you want to do the non-oxygens, non-hydrogens first. So let's look here. So basically you've got phosphorus and you've got calcium to deal with that aren't oxygen and hydrogens. So looking here, we start off with 1 calcium, 3 calciums on the product side because the arrows are cut off. So as a result, we're going to need to add 3 calciums over here. So I put a 3 here. And once again, this is a guess and check or trial and error, see what works. So now I got 3 calciums. I got 3 calciums to finish with. So I'm good with my calciums. I look at my phosphoruses. I start off with 1. I finish with 2. So to get the phosphoruses balance, I'm going to put a 2 here in front of the H3PO4. All right, so now I've got everything set except for oxygens and hydrogens. It really doesn't matter which one you pick. If you look here, hydrogens in 1, 2, 3 places, oxygens in 1, 2, 3, 4 places. So it's probably easier to do the hydrogens, but it really doesn't matter. So if I look here at the hydrogens, I've got 3 times 2 hydrogens. So I've got 6 hydrogens here. I've got 2 times 3 hydrogens, so I've got 6 hydrogens here as well. So a total between these 2 compounds on the left side, I have 12 hydrogens, 6 and 6. This over here, I only have 2. So to get this to 12, I'd have to put a 6 coefficient in front of it. So now my hydrogens are balanced. Okay, so now I have to look at my oxygens, and hopefully a lot of times the oxygens will shake out, or if they don't, it's pretty easy to fix. So here I've got 3 times 2, which is 6 oxygens in the CaOH2. So 6 oxygens here. I got 2 times 4, which is 8. So I've got 8 and 6. So that adds up to 14 oxygens on the left side. If I come over here, I got 2 times 4 oxygens, which is 8. And I got 6 times 1 oxygens, which is 6. So 8 and 6 is 14. So the oxygens work out. So it works out really well for us in this case. This is one of it looks to be super complicated. It's really not if you just kind of attack it element by element. The other question that you could ask is, what is the sum of the coefficients when this equation is properly balanced? So it's 3 plus 2 plus 1 plus 6. So that's 7, 10, 12 would be the sum of the coefficients. Okay? All right, so that's our practice bell ringer. I'm going to roll into another practice review of last class. Write out the following chemical reaction or equation. So I give you the reaction today. After today, I don't have to give you the whole reaction. You'll be able to figure out what they are, and this is where it takes practice. All right, you can't get starstruck or awestruck by the process. Just do it. It's not that bad. So in this case, I'm telling you, hydrogen gas reacts in the presence of oxygen gas to explode and produce liquid water. So take it step by step. So here, hydrogen gas, how do we write hydrogen? Now, the thing that you have to remember about hydrogen is it is diatomic. So you got to write as H2. Now, I'm putting in the phase here because it says it. It doesn't really matter if you do, but we'll just try to do it when we can. So you got H2. Remember, hydrogen's diatomic. Now, it says in the presence of oxygen. So what that means, hydrogen with oxygen. So how we write that is we put a plus sign. Then we have to write oxygen. Now, oxygen's an element, so we have to think to ourselves, is oxygen diatomic or not? Hopefully you remember oxygen is diatomic. All right, they tell us it's a gas, so it's going to be O2G. All right, so it's O2 gas. All right, to explode and produce liquid water. So that means it's going to produce something, so that means it's in our arrow. And then water, it's going to make water. So it's going to make liquid water, so we're going to have a little L at the end. But water, hopefully you know by now, is H2O. All right, and we have here. And then the explosion part, and we haven't really gotten to this. We'll talk about it more later on in the year. We talked about it a little bit earlier in the year. We could add energy to it if we really wanted to get super good at writing these equations. If you didn't put the energy in it right now, that's fine. Remember, energy on the right side of the arrow is given off, so that's an exothermic reaction. All right, this is a very exothermic reaction. This is the reaction that actually propels space shuttles into space. They have hydrogen tanks and oxygen tanks. They make water, and lots of energy. Okay, so that's practice writing the reaction. Now we're going to get the question to go along with it. You want to make 10.5 grams of water. How many moles of oxygen would you need? So this is kind of a direct piggyback of what we did last class. Okay, so to do this, you're going to need to do one of those charts. But before we do the chart, we have to balance the equation because we have to have a balanced equation. And if we look up here, we start with 2 hydrogens. We finish with 2 hydrogens, which is good. All right, but we start with 2 oxygens and end with 1. So that can't happen. So we have to do something. So we're going to have to put a 2 here in front of the water. All right, to get the oxygens balance. All right, now we have 2 oxygens to 2 oxygens, we're good. But now we have 4 hydrogens we finish with. We start off with 2, so to get this to 4, we put a 2 in front of it. Okay, so now we have the equation balanced, so we're good to go. So now we do that chart where we got the mass GFM moles. So it looks like this. I did it in black today. Okay, and now we put in what we need to get to and what information they give us to start with. So we know we want to make 10.5 grams of water. Water is going to be, you want to make 10.5 grams of water. How many moles of oxygen do you need? I apologize. I froze there mentally because I know I just wrote these notes. So question mark, we need to know how many moles of oxygen we need. That's our endpoint. And our starting point is they give us 10.5 grams of water. All right. Okay. So now we have to go from grams of water to moles of oxygen. We cannot do that directly. Okay, so we have to go, all conversions on all these stoichiometry things, we generally have to go mole to mole. All right, so we have to get grams of water to moles of water. To do that, we need the GFM. Hopefully by now you know 2 hydrogens and 1 oxygen adds up to 18 grams per mole. All right, to get to moles, we basically divide 10.5 by 18. So you should do that on your calculator right now. All right, 10.5 divided by 18 is 0.583 moles or something really close to that. Notice I give 3 digits. All right, this 0 in front doesn't count. We need lots of digits. We have 3 digits in each here, so all of our answers should be. Okay, now to go from moles of water to moles of oxygen, we have to do that mole ratio or that mole calculate, the mole ratio, where it's moles given, so 0.583 over 2 equals X, because we don't know the moles of oxygen, over its coefficient, which in this case is 1. All right, so I didn't set up that fraction on here, so it's 0.583 over 2 equals X over 1. All right, so basically what you're going to have to do is you're going to have to divide this. That's half the number of moles of oxygen versus twice as many moles of water. So basically this number divides by 2. All right, when you divide that number by 2, you get 0.292 moles. Okay, so that's how many moles you would need. Now we could go on and we could say how many moles, how many grams of oxygen that would be. You could ask for how many grams of hydrogen and things like that. But those are just all kinds of different problems that you can see. Just wanted to kind of refresh your memory, show that to you again, try to clarify some things for you. Okay, now we get to move on to our types of reactions. All right, I'm going to do this as quickly as possible. So you're going to probably want to pause the video so that you can write things down. Writing things down is super critical for retaining information. Okay, so the 5 types that we're going to have to be exposed to at this point in time are synthesis reactions, all right, decomposition reactions. These are exact opposites of each other. You know what a synthesizer does? It puts things together, all right? So we're going to put things together in a synthesis reaction, and then the opposite of that happens in a decomposition reaction where we actually break things apart, okay? So those are actually opposite direction reactions for each other. All right, there's what's we called combustion reactions. We have talked about combustion reactions, but we really haven't identified what they are. All right, and then the new terms for us at this point in time would be single replacement reactions and double replacement reactions. And just like the name says, in a single replacement reaction, one thing is replacing another. In a double replacement reaction, 2 things are replacing each other. Okay, so those are the 5 reactions. I'm going to go through some examples and what we have to deal with these things. And like I said, you'll be doing a lab next week, experimenting with these 5 reactions. It's a pretty fun lab. You get to make things. It's one of the few labs we get to let you explode things. So it's kind of cool. All right. But you need to be able to identify the reactions based upon how they're written out. All right. And if I only give you the reactants and tell you it's a synthesis or a decomp or a combustion or a single replacement, double replacement, you'd have to be able to write the products. All right. So this is where we kind of up the ante in chemistry, where you really have to know your stuff to be able to do this. Okay. So first things first, we have synthesis reactions. I have a little cartoon down here. This is a cartoon that, I don't know, I got from somebody somewhere at some point in time. If you are an artist and you would like to make a better one, please do so. Let me know. All right, but if you look here, you have a skinny bird and a worm makes a big bird. Okay, so two things, and the way we talk about synthesis reactions are two things making one thing. Okay, so a synthesis reaction occurs when two substances, usually elements, combine to form a compound. You can have compounds form bigger compounds, but a lot of times it's elements. All right, other names for these are combination reactions or addition reactions. This addition reaction we will revisit when we get to organic chemistry. Okay, but they're all synthesis. They're literally just putting things together. But you have to put them together correctly. You can't just randomly throw them together. We have to remember our crisscross rules that we've learned already this year. So generically speaking, it's one reactant plus another reactant will make one product. Okay, so that's what a synthesis reaction is. Like I said, I'm going to go through this so that there's not a lot of pause time. Make sure you hit pause and write things down, and then so you can listen to me as well. All right. But, one version of this is element A plus element B will make a compound A2B. And why it makes this compound is determined by what the oxidation numbers these things are. All right. You could have AB2. You could have A3B, AB3, depending on what the oxidation numbers are. All right. This isn't balanced. You then have to put a 2 here. I didn't balance this generic equation. But here's an example of a synthesis reaction. We've seen it already today. Hydrogen reacts with oxygen to produce water. All right, you do have to balance this. We did balance it already. So it's a 2 in front of the hydrogen, 2 in front of the water. But you're taking two elements, they're combining and forming a compound. All right, you can't just throw the elements together like H2O2 or HO. Remember, you have to look at the oxidation numbers. You have to crisscross. You have to jump when we write the compounds. All right, here's another one. So here, this is what actually happens in soda. All right, you got carbon dioxide in the presence of water. All right, and what happens is the carbon dioxide will react with the water in some cases, and it'll actually make carbonic acid. This is H2CO3. All right, this is actually what regulates our breathing rates in our body. Like if we start breathing heavier or faster or slower, all right, it's the relative amount of carbonic acid in our blood. All right, it's kind of a cool thing. If you've taken Living Environment, hopefully they talked about it a little bit. If you haven't taken Living Environment, you will talk about it. And you'll have an idea what they're talking about in there. Okay. I don't remember if I balanced this one. I didn't. Is it balanced? 1 carbon, 1 carbon, 2 hydrogens, 2 hydrogens, 3 oxygens, 3 oxygens. So the reaction as itself is already balanced. So going forward, I could give you carbon dioxide reacts with water and just say, what is this product going to be? You would have to recognize that it's carbonic acid. All right. I would tell you also that it's a synthesis reaction that they're going to combine. Okay. All right. So that's our synthesis reaction. That's one of the 5 that we have to know. Decomposition reactions are the exact opposite of this. So here's our cartoon down at the bottom. We've got an egg, breaks open, and makes a baby turtle in this case. So in this case, and I'm waiting for the thing on the bottom to disappear, you have one thing making two things. So if you look at synthesis reactions, it's two things making one thing. In a decomposition reaction, it's one thing making two things, or 3 things if it splits into 3 things. All right, so decomposition reactions occur when a compound breaks up into the elements or simpler compounds. All right, more than likely than not, it's going to be elements though. Generic written reaction is one reactant will make a product and a product. All right, whatever those products may be. Okay, so in general, so I have my general reaction here like I did before. In this case, I have compound AB, and it's going to split apart into A plus B. Now, it could be one of these elements is diatomic, and it could be AB2. All right. If these elements are diatomic, remember you have to write the subscript 2 for them. And then we'd have to balance it and things like that. But I'm trying to give you all the things that can be, pitfalls when we're doing this stuff. So here we go. We got, in this case, sodium nitride is going to decompose into sodium and nitrogen. And you can see here, nitrogen being diatomic, we have to write the subscript 2. Now I did put solid and gas here. You would not have to worry about the solid and gas part. All right. But it's just something that it's information if you need it. Okay, so we have to balance this now. We have 3 sodiums here, 1 sodium there. So did I balance? Oh, I'm sorry. I balanced it a different way. I went with the nitrogens first. So you got 2 nitrogens here. You start off with 1 nitrogen. So you put a 2 here. Now we have 2 nitrogens. All right. Now we got to put, why did I put a 3 there? Ignore that 3. I don't know what's going on with that. And then we have a 6 for the sodium. I don't know what I did with that 3 there. I got to get that off. I apologize about that. Okay, so you need a 2, a 6, and a 1 would be this one balanced. N2O decomposing. What's N2O going to decompose into? So this one you should be able to get at this point in time. It's going to decompose into nitrogen and oxygen. So it's going to be N2 plus O2. They are both diatomics. All right, is it balanced? No. Actually, is it balanced? No, it's not. So we need a 2 here, and then we need a 2 here as well to balance the nitrogens. Okay, so decomp and single replacement are pretty easy to identify. Decomp has one reactant. Reactants are things on the left. Synthesis have one product. All right, and that's the easiest way. You just look at it kind of what I call big picture. Just look at this general reaction. Don't look at all the little components in there. Okay, combustion reactions. Combustion is another name for fire or burning. All right, and combustion can happen in a quick fashion or it can happen in a slow fashion. All right, it just depends on what's burning and what are the environmental conditions around it. All right, but generically speaking, a combustion reaction is an organic reaction. All right, but it's any organic compound. Think of things that burn: paper, wood, gasoline. All right, any other fibers, but all those things that are going to burn are going to be organic compounds, meaning they have carbon in them. And for something to combust or something to burn, it needs oxygen. All right, it needs oxygen, and the products of every combustion reaction are carbon dioxide and water. The only way you would get something different is if you had limited oxygen, then you would make carbon monoxide in water. All right, but you actually do make water when you make a fire, but it's definitely not enough water to put out the fire. Okay, so here, this picture, we have a fuel, which is our Bunsen burner. The fuel is methane, which is CH4. All right, in the presence of oxygen in the air, as long as it's got a spark to start, it will burn and combust. Okay, and I will show you a demo next week or sometime in the near future where I do a methane mop. That's pretty cool. But methane is CH4 plus O2. All right. Now you can write the products from this point. So here's our organic compound in the presence of oxygen. It will make CO2 and water. Now this is the products. These things in blue are constant in every single combustion reaction. All right. Now all you have to do, and sometimes the hard thing to do, is to balance combustion reactions. Sometimes they get a little bit challenging. Like you get up into here, like you get into like C10H20, and then you got to balance this out. It just takes a little bit longer. All right, so looking here, we got one carbon, we're good. We got 4 hydrogens and 2 hydrogens, so we got to put a 2 in front of the hydrogens here, or in front of the water, I mean. So now we have 4 hydrogens. So now we finish with 4 oxygens. So you got 2 here and 2 here. So you're gonna have to put a 2 in front of that one. Okay, and we could do, and the reaction's the same. So how I tell you to remember combustion reactions, look for oxygen as a reactant, and products are carbon dioxide and water. Okay, single replacement reactions. These are when one element replaces another in a compound. Somebody came up with an analogy, you're at a dance, or, there's boyfriend, girlfriend, whatever. There's partners or couple. All right. And one person kicks out the other person. And what you end up having is a new couple and a new thing kicked out. Okay. If you take Miss Erickson, she calls this relationship chemistry. I don't really go into relationship chemistry, but it's specific as to who can be kicked out, though. All right. I in this cartoon, they draw them as males and females. All right. And when we're dealing with it, we're going to talk about metals and nonmetals, or more specifically, positive ions and negative ions. A positive ion can kick out a positive ion, a negative ion can kick out a negative ion, but a positive ion cannot kick out a negative ion. Okay, because you need both to make a compound. You need a positive ion and negative ion to make a compound. So single replacements occur when one replaces another in a compound, and they can occur on their own, which is called spontaneously, if a certain condition is met, or you can force them to occur under other conditions. All right, but this is a new reference table that we're going to talk about. It's table J, and these things will only occur. A single replacement will only occur spontaneously or on its own when the single element is more reactive. So when the thing by itself is more reactive. So I'm just going to pop up table J here. I'm not going to leave it up because we can't see the rest of the slide, but this is what table J looks like. So let's say we have zinc. So find zinc. Zinc is here. Zinc reacting with hydrochloric acid. If you remember what hydrochloric acid is, it's HCl. All right. Now, zinc is a metal, so it's going to be a positive ion. And HCl, the positive ion, is the H. So we find H on here, all right, which is down here. Since zinc is more reactive than the H, zinc will kick out the H in the compound and H will be left by itself like this person over here. And then zinc will make a compound with the chlorine. All right, and you have to go by your crisscrossing rules to do that. So the only way that a single replacement reaction will occur is if the single element, find it on this table, whether it's a metal or a non-metal, more often than not, we deal with metals, is more reactive than the element, the like element in the compound. So if it's a metal, it's a positive ion. If it's a non-metal, it's a negative ion. So you're looking for, in a compound, the positive ion is the first one. So you're looking for this to be more reactive than the single one. Notice down here, hydrogen, and it tells you down at the bottom. I can't go down at the bottom because this little Google thing pulls up. It's based on hydrogen as a standard. It's not, hydrogen's not really a metal, but it does act like metals because it does have a positive ion. So we always have to check to see if the reaction will occur. All right. So now we'll move on from here. So what I was saying before is a metal can replace a metal, or a non-metal can replace a non-metal. And we can say metals or non-metals, or you can say a positive ion or a negative ion, because that's really the important thing. You have an element and a compound. It's going to make a different element and a different compound. So if you look down here, you have an element and a compound. It's going to make a different element. Notice the thing stuck out by itself is different than the one that we started with. So a different element, and then you have a different combination or a different couple. Okay. So here, generically doing in the AB stuff, so A plus BC makes AC plus B. If A is a metal. So if you're looking here, here's the compound. If A is more reactive than B, then B will get kicked out, and then AC will make a compound, and you have to go by your normal crisscrossing rules to figure out the formula of the compound. All right, here, if A is a non-metal, so now A is going to kick out the second part of the element of the compound, and in this case, the C. So the C gets kicked out, and then the compound's made with B and A. All right, so it depends on if it's a positive or negative ion or a metal or a non-metal, and you always refer to table J for it. All right, so remember the cation always goes first in the compound. Cation is the positive ion. That's just remember from before. So when water splits into ions, and another thing, a side note with this is you got to remember that water will split into hydrogen and oxygen ions. It'll split into H and OH. Hydrogen hydroxide. I don't know why I said hydrogen and oxygen. It'll split into H and OH, and that's something that we introduce here and we'll deal with when we get to acid-base chemistry, because that's an acid ion and a base ion. All right, so, and I didn't give a lot of examples in this one intentionally because I just don't want to take up a lot of your time. All right, so here we go, double replacement. They did this one here to make it different, I guess. They have some person, a face and a face with two different hats, and they swap hats. All right, you can think of it as two couples swapping partners, so to speak. All right, like the wife swap, if you ever watched the wife swap TV show. All right, but double replacement reactions, they got to have soluble compounds. All right, so these will all happen in solution only because you got to make the ions. All right, so one of the steps we have to take into consideration with double replacement is to make sure that the compounds are soluble. So we'll have to refer back to table F, or I don't know if we've talked about table F this year. All right, but we will. All right, so most will not occur unless they're soluble. All right, and because they have to form ions for these things to happen. So generic form of this is compound and compound will make product and product. All right, different compound, different compound. So here you got A, B, C, D makes 80. Now it's very regimented at how you can go. This is the positive ion A. It can only make a compound with a negative ion D. So that's why you got AD. Now I made it very simple here. I didn't put any subscripts because I didn't want to get into the crisscrossing part of it, but it could have subscripts depending on what these ions are. And then because A formed a compound with D, that means C, being the positive ion, has to form a compound with B. And that's why it's got to be written CB and not BC. Okay. All right. So situations where these reactions will occur. Sorry, I went a little bit quick there. Situations where these reactions will occur are when you look at table F and the reactants are soluble. So this is the first time we deal with table F. Table F is in the front of your reference tables, second page, I believe. And it gives lots of information, but not in the easiest fashion. Let's put it that way. So if we look here, so we have ions that form soluble compounds in this chart on the left. All right, we have ions that form insoluble compounds on the right. So for a double replacement reaction to occur, they have to be on this side. Does that make sense? All right, and if it's not going to occur, they would be over here. All right, there's general trends. You can see here, like group 1 ions are always soluble, ammoniums are soluble, nitrates, acetates, carbonates, chlorate, or hydrogen carbonate, sorry. chlorates, halides, and sulfates. But if you get down here, there are exceptions for the halides and the sulfates. All right. And then over here, ions that generally are insoluble are things called carbonates or chromates or phosphates or sulfides or hydroxides. But there are exceptions for these. All right. One of the best things I can tell you to learn is look to find a group 1 ion in the compound. If it's got a group 1 ion, such as a lithium, a sodium, a potassium, or rubidium, it's going to be soluble. All right, because that's a lot of these exceptions over here. It must contain a group 1 ion. Ammonium as well. All right, ammonium is another one that's soluble in virtually everything. Okay, so let's say I give you the compound sodium chloride. All right, sodium chloride, and you got to find it on here. Now, sodium chloride has two things you can find on here. You can find sodium, which is a group 1 ion, and you can find chloride, which is down here as a halide. So, sodiums are always soluble, so you know the answer there. But if you found it by the chlorides, you'd have to make sure that sodium's not an exception. So the only time a halide's not soluble is when it's with silver or lead or mercury. Okay. Another compound, let's do calcium hydroxide. Calcium hydroxide. So you're looking at calcium. Calcium's a group 2 ion, so it's not a group 1. Calcium's not ammonium, calcium's not nitrate, calcium's not acetate, calcium's not hydrogen carbonate, calcium's not chlorate, calcium's not a halide, calcium's not sulfate. So calcium can't be found here. Can calcium be found over here? Nope. All right, now I said hydroxide. Hydroxides over here are generally insoluble, except when found with a group 1. Calcium's not a group 1. Or with calcium right here. So this is an exception. So that means even though normally hydroxides would be insoluble, because calcium is listed here, this is going to be a soluble compound. All right, so calcium hydroxide is actually soluble in water. Okay, and that's what it means. Aqueous means soluble in water. And we can go through all kinds of examples on this. So I'm going to put this up here. I'm going to give you these 8 compounds. I'm going to ask you to circle or write down the ones that are soluble. This is where you should pause the video. I will pause it on Edpuzzles to ask you. All right, but I will tell you there are 3. There are 3 compounds here that are soluble in water. Okay. And when you do it, so you look here, I will tell you this first one, NH4OH, is soluble because it's got ammonium in it. All right. Na2S is soluble because it's got a group 1 ion in it, which is sodium. All right. And then the last compound that is soluble is strontium hydroxide. Hydroxides are generally insoluble, but strontium is listed here as an exception. So all of these other ones, barium carbonate is insoluble because it's carbonate. Aluminum hydroxide is insoluble because hydroxides are insoluble and aluminum's not listed as an exception. Lead chloride, chlorides are generally soluble, but lead is an exception, so it's insoluble. And then magnesium phosphate, phosphates are generally insoluble. Magnesium is not a listed exception because magnesium is a group 2 ion. Okay, so when you're doing these double replacement reactions, you have to first check to see if it's going to work. And how we do that is we look at table F for the reactants, make sure the reactants are that. Will this reaction occur down here? So you got 2Ki plus PbNO3. And I purposely didn't put the, if it's soluble or what phase it is down here. So if we look here, so Ki is a group 1 ion compound, so that's definitely going to be soluble. PbNO3, nitrates. Do you see here? Nitrates are right here. There's no exception. So both of those are soluble, so they will occur. All right, I look at potassium nitrate, and this is something we'll check later on in the year, but we might as well do it now as practice. Potassium nitrate is a nitrate and a group 1 ion, so it's soluble. And lead iodide. Iodide is an iodine with lead is insoluble. So it's going to make an insoluble product. Okay, and that's true to form for most double replacement reactions. One will be soluble product, one will be insoluble. Situations where it'll occur, a reaction will occur if one of the products is a molecular substance such as water. I'm not too concerned about that. But here, predict the products. So this is the last thing we're going to do today. So we have to be able to figure out the products. First things first, figure out if they are soluble. I will tell you right now to save time for you that all of these are soluble. You don't have to look on table F. If we were in class, I would make you, but I'm just going to kind of speed up the process. All right, so here, H is the positive ion. The positive ion in NaOH is Na. All right, so H is going to make a compound with OH. That's going to be H and OH is water. And then sodium is going to make a compound with fluorine. They both have a 1 oxidation number, so it's going to be NaF plus HOH. All right, so that's the crisscross jump. All right, here, H, this compound splits at the H and the NO3. So H is going to make a compound once again with the OH. And you'll see that a lot of times that water is one of the products. HOH is one of the products. Then you're going to make a compound with K and NO3. K is a +1 oxidation number. NO3 is a -1 oxidation number. You crisscross jump, you get KNO3. Okay, these are balanced as written. So we don't have to do anything to fix them. Oops, sorry. And then we have H, once again, going to make a compound with OH. So it's going to make that water again. And then we have a compound with calcium and chlorine. Now, calcium is a +2 ion. Chlorine's a -1. When you crisscross jump, you're going to get CaCl2. All right, so that's why this compound is different. All right, now we look at these things. Are these things balanced? We got 2 chlorines. We have 1 chlorine to start with, so it's not. So we got to put a 2 there. All right, we now have 2 chlorines to 2 chlorines. We have 1 calcium to 1 calcium. We have 2 oxygens to 1 oxygen. So we probably got to put a 2 over here. And now we have 4 hydrogens to 2 hydrogens plus 2 hydrogens, which is 4. All right, I get this is a lot of stuff thrown at you. Please listen to this. Please do the work. Please practice this so you're good to go. All right, and that's it. We'll see you.